Back to the exciting discussion that we are having on statics. This is part 2 of our unit in Project Lead the Way's 2.1 statics unit. So in the last section we talked about centroids and how we calculated the centroid of complex shapes and why that's important. Now we're going to move into talking about structural member properties. And what do I mean? What do I mean by that? We're talking about basically the stiffness of materials and how we can calculate how stiff a material is and how much it's going to deflect or bend when we apply loads to it. Statics is all about applying a load or applying forces to objects, and this is going to show us how to resist those loads. Or it will tell us how our objects will resist those loads. And the main thing we're going to worry about is that the resistance to a load or the stiffness of an object, it depends both on its geometric properties, so its shape, an object's cross-sectional shape, and then also it depends on the material itself and its material properties, because some materials are just stiffer than others. So let's get started. So before where we're going to start is talking about moment of inertia. That is symbolized by the letter I. And it is a mathematical property of a cross-section that gives important information about how that cross-sectional area is distributed about a centroidal axis. So basically it's saying when I calculate this using the math that we're going to be showing here, our units will be in inches to the fourth. And what it's basically saying is, depending on how my object is shaped, that tells me how much or how stiff it is. And the higher the number that you get from a moment of inertia, the greater resistance to deformation or the higher stiffness. So higher the number, higher the stiffness. And moment of inertia, key thing to remember here is it is based on an object's geometry, what it looks like from the end. And so in the pictures there we show a diving board versus starting blocks in a swimming pool, and the way these objects are shaped in these pictures. So the diving board is a long, skinny rectangle, whereas the diving blocks are shorter, thicker squares. The shape of those is what's contributing to the moment of inertia of these objects. Doesn't matter what they're made of, it's strictly the shape. So if I look at the exact same wood board here, it's made out of Douglas fir, it's 8 feet long, and it's a 1x6, or 2x6, excuse me. The 2x6 is actually 1.5 by 5.5. So this 2x6 in configuration A is on its end, so it's vertical, and in configuration B, it's on its side. So when it's vertical, it's considered a joist, and when it's horizontal, it's considered a plank. Now, I'm not sure if you can see the end of this, so I'm going to turn me off here for a second. And when I do that, you'll see that the width and the height are the same, but because the joist is vertical, my width is the 1.5 inches and the height is the 5.5. Width, height, and areas are all the same. So what happens when I do moment of inertia with these, or which one is going to be stiffer? Well, we'll find out when we calculate. Some of you might be able to take a good guess as to which one is going to be stiffer and which one will bend more. So the only distinguishing feature from A to B is that A is vertical and it's considered a joist, B is horizontal. What happens here? All right, so if we do what's called the stress test, this is something you could do in Autodesk Inventor or any other CAD software. It shows, the red shows higher deformation. Well, the plank deforms more or bends more than the joist does, and that's because of moment of inertia. So how do we calculate this? Well, when we lay out a joist as such, if we look at, I can't go back apparently. Okay, well if you look at this, this is the joist configuration. It's vertical, straight up and down. The base is considered the lower part, the height is considered the height of it. And when we calculate the moment of inertia for a rectangle, we use this equation. We always use base times height cubed divided by 12, where the base is always the horizontal portion and the height is always the vertical portion. So no matter how how you lay this out, base will always be along the bottom, height will be along the top. So for, and the other thing to remember is you're only cubing the height. So you're taking base times the height cubed, and then divided by 12. So if I look at beam A, where it's vertical, my base is 1.5, my height is 3.5, so 5.5 cubed times 1.5, all that divided by 12, gives me a moment of inertia of 21 inches to the fourth. When I flip the beam, and now it's laying on its side, now my base is the 5.5 inches, and my height is only 1.5 inches. So because the height cubed is such a smaller number, my moment of inertia ends up being a much smaller number as well. So when I compare 1.5 inches to the fourth to my previous 21 inches to the fourth, that's a pretty significant difference. So that's why there's so much more deflection in beam B. My moment of inertia is significantly less. 14 times less, in fact. All right, so there's composite shapes that are used in structural design. Why do you think that is? Well, if you look at all these different shapes, it's important to think about moment of inertia. So we do a lot more with less and by using less material, that ends up saving a consumer money. So if I look at this rectangle, and my area is 10, my area of the middle one is 10, and my area of the right rectangle is 23.8. So I have the exact same amount of area in my left two than I do on my right one. So that means that the left two are cheaper than the right one, just because there's less material. Which shapes are the strongest? So let's compare their moments of inertia. So if I have moment of inertia for the left one versus the right one, I have more material. They're the exact same shape. They're rectangles. They're facing vertically like that. So they're considered joists. My moment of inertia is much higher where I have more material. But if I look at the middle one with a smaller area, I have almost the same moment of inertia as the right one, and I'm using about half the material, a little more than half. So composite shapes help you to be stronger using less material. So now that we've talked about the geometric properties in moment of inertia, we're going to talk about what's called modulus of elasticity. This is a material property. So it doesn't matter, well, the shape does matter in strength, but in general, when we're comparing materials now, modulus of elasticity is how stiff a specific material is. So before it was a Douglas fir beam that was just shaped two different ways. Now we'll be comparing like Douglas fir to steel or aluminum and see how different they are. So modulus of elasticity, or symbolized by the capital letter E, is the ratio of the increment of some specified form of stress, and we won't go into that anymore. Basically, what we have is modulus of elasticity is the stiffness of an object due to its material chemical properties. And modulus of elasticity is going to be, generally, it will be a given number for you. You'll be given the material property. And again, with a higher modulus of elasticity, we have a higher resistance to deformation. These are generally large numbers, like to the millions of psi is the labels that you'll see in modulus of elasticity. So if we compare shapes here, we have the exact same size beam. It's again a 2x6, 8 feet long, same areas, same modulus of elasticity because it's all the same shape, but now they are different materials. One is ABS plastic and one is still Douglas fir. The difference is material, and when I look, even though they're the exact same shape with the exact same moment of inertia, the wood deflects more because it has, or excuse me, the plastic deflects more because it has a smaller modulus of elasticity. So if you look at the modulus of elasticity of our wood Douglas fir, it is 1.8 million psi compared to 419,000 psi for the plastic. Now when we know both moment of inertia and modulus of elasticity, that's when we can start estimating and calculating how much these beams are going to deflect. In addition to knowing those two things, we need to know the amount of force that's being applied, and we need to know its overall length. And then what we do is we set it up in what's considered simply supported, a simply supported setup. So simply supported means that I have support on one end and support on the other end, and then I'm pushing straight down in the middle. And that's what a simply supported setup means. Let me delete these to clear this off. So if I have it simply supported and I know these things, I can use this equation. Delta max, this triangle, delta is the Greek letter that looks like a triangle. Delta max is the deflection, and that is equal to the force applied times the total length of the object cubed divided by 48 times the modulus of elasticity times the moment of inertia. And you have to make sure you do all of this and then do all of this, and then you could divide the two, or else you make sure you're using your parentheses properly in your calculator. So for beam A, delta max, I'm given the length, I'm given the moment of inertia, I'm given the modulus of elasticity, and I'm given the load, which would be the force. So what do? I just take them and plug them in. 250 times 96. Because these are in PSI, I need to make sure this is in inches, and I'll be sure to remind you guys of that. 96 inches cubed times 250 pounds, and all of that will be divided by 48 times 1.8 million PSI times 20.8 inches to the fourth. And when you plug all of that in properly, you should get 0.12. So I would recommend practicing typing this exact setup into your calculator to make sure you get 0.12 and make sure you are understanding how you are typing things in. For beam B, my deflection is 0.53, so I get a larger deflection because I have a smaller modulus of elasticity. So that's the discussion of geometric properties combined with chemical or material properties in determining how stiff